Okay, welcome everybody to Braden's session today. He's going to be talking about computational thinking, which is that big, but actually not as scary as it sounds concept that is running through the new curriculum. And he's going to be focusing mostly on Div 3, but it'll be kind of fun to see where he sees things evolving because it sounds like it's much bigger than that. And just an introduction to Braden. We actually don't know each other very well, but he was recommended to us by Mike and Kathy up at the university, Mike Carbonaro, who you may remember from your university days. He taught many of us. And they said, oh, he has such a good knowledge of computational thinking. You really need to have him present courses. And what I love about Braden's sessions myself is he isn't like a consultant that's been out of the classroom for a bit, like me. But he's the real deal. He's teaching at Victoria School in Edmonton, so he knows, like, he is in the middle of the daily grind of everything to do with teaching, and his stories are real, and it's kind of like what he did yesterday or today or tomorrow. So welcome, Braden, and his wife is a grade 1 teacher.
Yeah.
Over to you.
Thanks for the great intro. I appreciate that. Yeah, we'll get more into it. This is just like a little preamble. This is going to be mostly focused on science and math, just because that's kind of where the curriculum aligns best. If you're not here for that, then we can definitely talk about specifics. But the general focus of this will definitely be more of a science math base. But yeah, we can talk about that as we go. Also, feel free to stop me, ask questions. It just makes the conversation better. But yeah,
Right, I forgot to say that part as moderator. Yeah.
Oh yeah,
he's easy, but if you put something in the chat, maybe he's in the middle of something and you have a question, you want to just jot it down in the chat. That's good too. We just want it to be an informal learning of the group.
There we go. Okay, perfect. Yeah, so this is specifically for Division 3. I do work at Victoria School of the Arts. This is like my third job. My second job, I TA at the U of A for the educational technology course, EDU 210, which is if anyone has been at the university for the past 6 years, I've been one of your TAs. So that's that. Yeah, we'll get started. We'll do introduction. We'll do a brief overview of what computational thinking is and what it means, and why it's not super scary. Then we'll talk about math with specific math outcomes that you can use computational thinking to cover. And then we'll do the same thing with science. And then, yeah, I'll take any questions. I'll take any questions as we go along as well. But yeah, that's the general idea for today. So yeah, I've been teaching at Victoria School for a decade, which is nice because as an art school, I get to really experiment. They're not super concerned with what I'm doing. I'm math science focused, so they kind of just let me do whatever I want. Nobody really checks in on me, so it's a nice thing. I am interested in technology and education, specifically media ecology, so how different media fit in into the classroom and what the trade-offs are and how the trade-offs can affect the environment, the learning environment. I did get a master's in that, so that's kind of where my interest is. And my goal is to give you some tools that are ready to go. So if you can come away with this with one tool that you can start using tomorrow or by the beginning of next term, then that's kind of my main point for this. It's also, again, this is beginner stuff, so it's more basic than if you have any experience with this, it might seem repetitive, but yeah, again, I think it's a really great just to have a solid grounding for where we're going to be jumping off to.
So I'm going to butt in for just a moment, just to kind of reiterate that. a little bit because, like for me, I do sessions on computational thinking as well. And what I want to, like a takeaway I have from Braden's presentations is that it's so interesting. So if you're doing work like this with colleagues, it's so interesting to see how other people present and the way they present, like the really basic information. I think there's that idea that people are always the best at providing professional learning when they're like one step ahead of the people that they are. And I mean, Braden is himself further, but for us to hear like how to present it at a beginning level is it's like helpful mentorship for us too, if we know some of this stuff.
Yeah, it really is helpful. And I wouldn't say that I went to school with people way smarter than me. I think I am only one step ahead, which is, yeah, which is a good thing for explaining. So computational thinking, just to be clear on what that means, it's a specific way of thinking about and solving problems. So people sometimes refer to it as thinking like a computer. It's just a habit that you can use to solve problems in different areas. So if you know how to think computationally and use the strategies that they outline, it can be helpful in different subjects and different ideas and different areas of life that you might not have otherwise thought about. So there is a large overlap between computational thinking and the curriculum now, but again, it's only going to get larger. I don't know if you guys have looked at the curriculum, like the new K-6 curriculum, but there's specific outcomes now about computing science. From all the way from K-6, there's a computing science unit in every class. So I'm anticipating that that will continue from grade 7 to 9 when we get a new curriculum. So that's kind of where we're starting off with. I'm trying to incorporate as many big picture ideas for computational thinking into the curriculum that already exists. It's not going to be as explicit for as Div 1 and Div 2, just because it's not there, but we can definitely use it effectively in our classrooms. So these are the main principles that the main ideas from computational thinking that can be applied. So pattern recognition is huge. That's a whole section of math. Is just that's a strand of math is patterns. So we're identifying similarities, patterns, and problems in the steps. So this is an important skill for all students, is just dealing with patterns. Then there's decomposition. So when you're building code, sometimes the best thing to do is break it down into the smallest part, and then kind of rebuild it back up. And this is kind of what math teachers do with algebra all the time. You do it in tiny little steps constantly. But that comes from, like, it doesn't come out of computational thinking, but they share that relationship together. And then there's collaboration as well. So this is huge in math and science. Coding and computational thinking is a collaborative endeavor. Usually, this is well known, like if for software engineers, if you don't know a problem, you can just Google it and somebody else would have solved the problem, and you can just rip the code, translate it to the coding language you're using, and like nobody claims plagiarism because all coding is plagiarism. It's just using the right plagiarism in the right places. And then it continues on. So logic is a huge problem. So thinking step by step, again, that's huge in math, as well as science, in terms of like the labs that we do. Algorithms are mentioned explicitly in the math curriculum currently, but all it is just creating and following steps, right? So a lot of people get freaked out by the term algorithm, but all it really is just a recipe. It's just a step. Do if this, then that kind of scenario. And the last one is tinkering. So tinkering is an idea where you just kind of play around and see what happens. So we'll get into a program that does this really well. But if you make small adjustments, you just do it to see what happens. You might go a little off of what you're supposed to do, but you can still get valuable learning experiences by doing that. So those are kind of the main computational thinking ideas that also align with grade 7 to 9. There are more, but the other ones I thought weren't as good a fit, and I thought 6 was kind of plenty to get us started. So the theoretical background behind this is constructionism. Constructionism means you're building models and then learning from building those models. So the goal here is to have students create an artifact, because by creating an artifact, then they can learn from making it, and they can also reflect on it afterwards based on the artifact that they can look in front of them. So for example, there's like a classic example, right? You build an atom, you learn about the atom as you build the model. Okay, that's a pretty basic example. What it might look like with computational thinking would be something like this, building a bunch of code. And the grades 3 to 6 curriculum specifically mentions block coding, which is what that picture is of. For anyone that doesn't know, block coding is just a type of coding where you're not going to be able to make syntax errors, whereas normal coding, if you're using a coding language, if you put a comma in the wrong place, it can mess up the whole thing. Whereas this kind of prevents those errors from happening and focuses on big picture ideas. So that's where the curriculum is like grades 3 to 6. So I'm anticipating that it's going to be somewhat similar and look like this. We will get into how to use these programs. It is not as intimidating as it looks. I promise. So this is a personal anecdote. So for physics 20, there's a part of the curriculum where I've taught physics. I was a physics major. That's kind of where my background is. Now I teach math and science and phys ed and bio and chemistry and just whatever they give me, basically. But I thought I was really strong in physics, definitely strong enough for physics 20. But then for one of my classes at university, I had to build a game I wanted to build a game that was based in physics 20 that would show what real physics would be like in kind of in space. So I built this game, and it was incredibly difficult for me to build this game, even though I thought I knew the physics backwards and forwards. I didn't, but I wasn't aware that I didn't know until I actually tried to operationalize what I was doing, until I actually tried to put what I knew into coding and like think about things computationally. So this is the thing that I had to write to that basically met this outcome, which ends up being very simple. It's 3 lines of code, and all you're doing is adding vectors. It took me so like you can literally see there's an x position plus a velocity, and then that's all you're doing. So literally the code is telling the computer program to add vectors, and I couldn't figure this out for so long. Like this little bit of code took me 3 hours to figure out how to do it. And as soon as I made it, I was like, oh my gosh, this is so obvious. All I'm doing is adding that, like it became super obvious after, but I didn't realize that I didn't understand the physics intuitively as I thought I did. So this is just the game that I made here. If you guys ever played Asteroid growing up, it's just Asteroid, but with real physics. So this is all it is. So like Asteroid with real physics, you know, you have to have the thing on, and as soon as you turn off the boosters, it's just going to keep going forever and ever and ever and ever, because that's what happens. The original game, you would stop for some reason. What else? Oh, every time you shoot like a bullet, you start moving backwards, because that's also physics. You can't just shoot something and not move, it not affect your motion. If you want to move backwards, you can't just go backwards. You have to actually have a booster in front of you to make yourself go backwards. So just like annoying pedantic things that that I thought was going to be super easy to get a completion for the course, and it ended up being like super eye-opening for how for how much I didn't know about something I thought I was really good at. So that's just the personal anecdote for that. Okay, Div 3 math. So grade 7 to 9 math. How can computing science fit into these ideas? And then I'll provide you a couple jumping off points for that. So these are the curricular processes that are it's in the front matter of the curriculum, but it's all there. So problem solving in patterns. So that's directly computational thinking, using different tools for learning and creating algorithms. That's huge. That's all that what I'm going to show you is. So that aligns really nicely with that part of the curriculum. Visualization, so making models and then it's helping to visualize the math is really great as well. And then reasoning using logic to solve problems, that's kind of inherent to computational thinking, which we already went over. Logic was one of the main things. Okay, so grade 7, these were the sample outcomes. I could have picked a lot of different ones. These were the ones that I thought we could kind of get started with. So in grade 7, they have to perform geometric construction, so perpendicular line segments, parallel line segments, perpendicular bisectors, angle bisectors, kind of just all these geometric things. Grade 8 was graphing and analyzing 2 variable linear relations. And then grade 9 is use a variety of technological graphing tools to draw graphs for data involving 1 or 2 variables. So this is these are just the sample outcomes from each grade, and I'll show you how to address each one of those. But the way I'm going to show you, it's not going to just address those single things. They can address a whole bunch of things. I just wanted to be clear that I am taking these ideas directly from curriculum. Okay, so for geometric constructions, the best jumping off point, especially if you or your students have never done coding before, the best thing to do is something called Hour of Code. So there's a bunch of resources called Hour of Code where they've collected a bunch of different games that take about an hour to do, and the students work their way through them. And in doing so, kind of learn coding and learn the yeah, it is perfect for, I usually do Hour of Code right before the break. I make sure I have a Chromebook cart and book it off for my kids so that all the day before the break, we're just doing Hour of Code for every class. It is a really nice thing for December. So like we said, we were talking about geometric constructions in grade 7. So if you teach grade 7, I have I'll share or somebody will share the slideshow with you, but everything is just linked in the slideshow. I'll just show you what it is. So it's coding with Anna and Elsa. They have a video, but all this coding is learning how to draw geometric shapes. So we're straight into math curriculum geometry. Okay. So for example, this is just showing how to create a single line. So move forward, turn right. I wish I could. Yeah. And then turn right by 9. Oh, actually, all I need to do is create a single line. So move forward, and then I press run. Great, done. So it's starting at the very lowest level where all you had to do is pick the right code, drag and drop it underneath, and press run. Okay, and once you get that level, you can move on to the next one. This is all free, by the way. Everything I present will be free unless I say otherwise. So now let's see if we can create 2 lines that are 90-degree angles to each other. So we have to move forward by 100 pixels, turn right by 90 degrees, and move forward by 100 pixels. So when we run that, and there we go. So now we're into stuff like this. And as I'll just skip ahead to like level 19, for example, you start to make different snowflake patterns, which are just repeating geometric shapes. Okay, and you have to learn the angles. You have to be able to use repeat blocks, which is logic. You have to be able to do a bunch of different things, but it's progressed in such a way that they're only learning one new block each time. So it's already, the scaffolding is already built there for you. Okay, so you don't have to go and learn coding by yourself. Everything's pretty much ready to go, right for grade 7. Okay. Are there any questions about this first little bit here? No? Okay, we'll just keep going. So that's great for grade 7. There's also this one, which is less like cartoony, less Disney. Where is it? We can launch the lessons here. And it just, again, it's step by step. We're writing programs. It looks a little bit, it's actually the exact same amount of difficulty. It just looks more complicated because they're taking the code. They're kind of taking more of a halfway hybrid between what actual coding looks like and what block coding looks like. So actually, just for a second, I'll just go back here. What's kind of cool is that if you have this code set up, you can just show what the code is. And it looks all very complicated when you look at it like this, but this is all it is. So it allows the kids to see, okay, this is actually pretty manageable when you break it down. Okay, it's actually not, so like that's the last level, that's the most difficult one. But even just back here, move forward 100. And then you have the annoying semicolon that people always miss. So that's all. It's really nice in that it shows what the coding actually looks like. And you can see this is kind of more of a midway point. Where here we can just continue. So modify the inputs to draw block to generate a blue square. So now instead of circle, I'm going to put square, and instead of red, I'm going to put blue. Press play, and there we go. It builds it, and then it just keeps going on and on like that. And then it also asks questions in between. So this one says, what is it, the type of shape drawn or the size of shape drawn? Well, it's the type of shape. So it allows me to continue. So it's really step by step. Sean, JavaScript. Sometimes with these like code games, it's kind of a mix between like Python and Java. Sometimes it's all Python, sometimes it's a bit of a mix, but yeah, it's usually one of those two, either Python or Java. So that's another example of hour of code. And for the higher levels, there's this thing called Desmos. I'm sure some of you know this already, but it's a really, really great graphing tool. It's not coding, but you still have to use computational thinking skills to be successful at it. Oh, good. Yeah, that's yeah. So in this case, it actually works for shapes and equations. So this is right back to geometry, where we can construct lines and we can make circles and we can make tangents and we can do all these things that are pretty straightforward with Desmos. We can get angles going. So between here and here, we can get the angles. We can get all these different things just by kind of playing around. And if you give the students an assignment, actually very similar to what it has here, it's the Global Math Art Contest on Desmos, where their goal is no longer to necessarily make like something like go through worksheets. It's to actually make art with the curriculum that you're trying to teach them. So you can set the guidelines and say, okay, you're going to make art with these shapes. Here are all the things you need to include in your art to be successful. But outside of that, it's completely up to you what you decide to make. Okay, so that is so that's there for the shapes portion, but there's also equations portion. So this is essentially just a really cool graphing calculator, but it's just browser based, so it works really well on Chromebooks, and it allows students to see right away without having to actually take the time to graph something, it allows them to show like right away, how do we tell what the y-intercept is? Like for example, if I just type y is equal to x plus 4, there we go. We can see, okay, that number is 4, and it seems like there's 0. Okay, it goes up in 4. What if it's -6? Oh, now it's down here. What happens if I add a 2 in front of the x? Oh, it makes it steeper. It makes it twice as steep. What if I add a half? Okay, less steep, right? So you can kind of play around with it. And you can even add quadratics, which is pretty cool. So like plus, where is it? There's all these formulas down here you can access. So plus, oh, there we go. Plus x squared. And now we are into like almost high school level. And you can play around with it, and you can still add, make different art using these graphs, which I'm sure you've seen. I think I remember my high school teacher making us do art with graphs on our TI-84s, which was not nearly as fun because it had a lot more typing. But yeah, you can do like a bunch of different stuff. You can even add like inequalities work really well. I know some students always have trouble with that, so there's an inequality. Yeah, so it's really a nice thing to use that students, if you give them, I'll give an example. A lot of people always say like it's good to think outside the box, but I think the best creativity comes from creating a box and then having people do things inside of that box to be as creative as possible. So for example, if you just give some students, say like, oh, you have the whole world in front of you to do whatever you like, that's too many options a lot of time. It's much better to restrict, and then you can see all the creativity that comes out of restricting the size of the box. So what ends up happening is you end up having to be more creative to do anything interesting while remaining inside of the box. So that's just, yeah.
I have a comment
What's
about
that?
that. So as you were talking there, Braden, I was thinking, I wonder if anybody in the room is wondering, and like this isn't the question, this is like the preamble. But if anybody in the room is wondering, okay, that's cool, I could try that. I don't really know what this has to do with computational thinking. But then as you were talking about it, one of the things that came to mind is that like you compare that kind of activity to the kind of activity in hour of code, and if computational thinking is, working towards those algorithms, in hour of code, you're applying an algorithm in order to solve a problem. But in this kind of activity, and that goes back to what you were saying about boxes, is that you've restricted the box. We're working with these tools in this particular way. This is our box. This is our environment that we're using. But now we are creating that art. And so what is going on in their head as a mathematical thinker and a computational thinker, that is what is happening in the background to create the art, rather than having an actual object that reflects the operationalizing of it in code. Is that correct? Does that make sense?
Yeah, you put that way better than I did.
Oh, well, no, I wasn't. I'm like, I think that's what he, but yeah.
Yeah,
Don't
no,
ask me to repeat it.
that's what I meant to say. Yeah, just like that.
That's really, it's cool. It's like that next level, and yet that's the next level is the real level. But we have to get there through, if we don't have the language of coding to start with, or that language of that thinking being made really visible,
Yeah,
then maybe we wouldn't get there. I don't know.
no, exactly. That's kind of the point with this, is like hour of code is a really good jumping off point for coding, but a lot of people, when I bring it up, they get intimidated by, oh, the students need all this background knowledge, or like I need all this background knowledge. So I'm just trying to make it as easy to get into and like start thinking about computational thinking ideas. So like you can, yeah, not everything with computation. That's the whole point with computation thing, is you can apply it to a bunch of different realms. Like you could even apply it, like what I just demonstrated, you could apply it to a graphing calculator, where even though there's no actual coding going on that you're explicitly doing, you still have to use the breaking steps down, do it step by step. What I just did there with the manipulating just to see what happens to the curve, like that's tinkering. That's all that is, right? So it's just the same ideas, but with a different kind of spin than just straight coding. Because if I like the thing with coding is that it is, well, actually, I'll talk about that in a bit because I think I mentioned it soon anyway. So that's it for the math. Now it's the science. So this is kind of where I teach right now. I teach grade 7 science. I've taught, yeah, grade 7, 8, 9, 10, 11, 12 science. Yeah, I couldn't remember if I did all of them, but I think I did. So the ideas in science are slightly different than the front matter in math. So the ideas in science, we have initiating and planning. So initiating and planning is so important when you're doing coding. A lot of people think it's just like you go straight to the computer and you start typing. And some people do that. But a lot of people actually think it out like on a whiteboard before they even try to code, because they have to get their ideas out in a way that makes sense to them, and then they code to those ideas. So initiating and planning is so important. And then we have science and technology, so using tools to help explain our world. If we use coding tools to make models, that's directly from the curriculum. We're using tools to explain our world, and then by making the tools and using them, we're able to communicate and understand on a deeper level than we otherwise would have. And then scientific inquiry, so problem solving, decision making, is really important for science. Decision making especially, I didn't talk about it, but evaluating is so important in computational thinking, because you might be stuck between two different scenarios. For example, you have a bit of code that works perfectly, but it's super long, which means it takes up a lot of space, and every time you use it, it might slow down, versus a code that doesn't work as well, but it's a lot faster. So those are common threads that happen all the time with coding, and you have to make an evaluative judgment, and scientific inquiry is all about that, right? There's no such thing as solutions. There's only ever trade-offs, and that is definitely really apparent with coding as well. And then again, we talked about communication and collaboration being so important for computational thinking, and it's right there in the science curriculum. So here are the ideas here. Sample outcomes. So for grade 7, again, the whole point for all of junior high science is basically using models. So typically what we would do is get the students to build models, physical models. But now we're going to try to translate that to building computer models and then learning based off of those. Okay, so with grade 7, I picked nature of thermal energy and its effect on different forms of matter using models, experimental evidence and models. And here was a model that somebody made on one of the apps I'm going to show you, where these were a bunch of particles, and if depending on how hot the fire was, the particles would move faster or slower, and like you could adjust the temperature, and depending on what the temperature did, the models would move faster. Okay, or yeah, so it was a really cool model that like a student made that did a really great job demonstrating, but I'm sure by having to make that model, they understood a little bit more about how it was working. So with grade 8, you're constructing and testing prototype designs and systems for fluids to apply force. So that's like hydraulics is the general idea there. And then grade 9, again, using models, explain the relationship among current, resistance, and voltage. And you have to construct and interpret drawings and models. So it says in the curriculum, you have to construct a model. It doesn't say that the model has to be a physical model, right? There's the great example from the movie Interstellar, where nobody knew what a black hole would look like until this movie studio could afford a better computer than the scientists could afford. And they constructed the model based off of math. And then they made the black hole in Interstellar. And based on that black hole, they were able to analyze it and make like 4 scientific papers based off of studying the model that they didn't have before. Even though the math was all there, as soon as it turns into a model, it's something different. Okay, so we're constructing models in the same way. The goal is to analyze the model, and then in the construction and analysis, you're able to better understand things. Okay, so for tech possibilities, if our goal for science is to build models, we can't do what with math. We can use Hour of Code, and that's really great. Hour of Code and code.org are related, but this is an entire coding course. Okay, so I'm going to show you kind of what that looks like. It looks very similar to Hour of Code, but it's a little bit different. And yeah, we'll get into it. So there is a learning curve, but the whole point is that they will be able to build something that they can then analyze later. And some teachers don't appreciate that they say, oh, coding isn't curriculum though. And it's like, yes, for now that's true. Coding isn't explicitly written in the curriculum. However, using wire and cotton balls to make an atom isn't written in the curriculum either. Like there's nowhere in the curriculum that says you need to know how to use a hot glue gun. But we just take it for granted that students should be able to do that. So this is just kind of an additional step where, yeah, they're not going to know how to make a perfect model every time right away, but it is a good jumping off point to be able to make those models that you want them to make. Okay, and then again, this is kind of a beginner step. So let's go to code.org and I'll show you kind of what it looks like. So this is called the Express course. They change it, they modify it every year to try to improve it. Yeah, coding is part of new grade 6. You're right. Coding is part of K to 6 now. I'm anticipating the next curriculum will have also 7 to 9. So yeah, you're right. It is part of the new grade 6 science. So this is the Express course. It looks very similar. It has a lot more stuff. It has these are all the courses. Each level only takes, depending on the level, early levels take 15 seconds, later levels take more time, depending on if you're having trouble. But again, this is free. If you get a teacher account, you can choose for your students, okay, I want them to do lesson 1, 3, 4. They don't need to learn about sprites, so we'll skip that. And then we'll do 7, 8, 9. And then, you get to pick which levels you want them to do, which is really cool. So just to get started here, again, we're starting very, very simple, where they have the number of blocks that it takes to be successful. And then you just have to attach the blocks here. And then we press run and it works. So again, this is just showing students step by step. We did the first level in 9 seconds. Okay, drag an extra move forward. So now we're showing that you have extra blocks in this little area. And then we're running. So it's very, very slow and it builds up quite slow, which is nice. The other good thing about this is if you have a teacher account, you can actually see the answer key to every single level. So this is not a program where you're expected to necessarily know how to do everything. You can, looking at an answer key, tend to figure things out, but it's not something that you need to have memorized. You don't have to go into level 20 and be like, okay, I know exactly what's happening. You can just look at the answer key to level 20 and go step by step and say, oh, this is why. But again, this is the general idea. So when I did my grade 9 science class, we made circuit models, but rather than using circuits, we did use circuits as well, but as supplementary, they had to make circuit models as a video game. on the next app that I'm going to show you, but this was the preamble. So I worked with their math teacher, so they had a few classes where they would do this in their math class, and then they come to me and they'd do this in their science class. And we did that until everyone was where they had to be to have the background knowledge in order to build something worthwhile. So the next thing is Scratch. So Scratch is fantastic. So Scratch is, you can think of it like block coding. It's very similar to this, but it's completely open. You have all the blocks available and you can do whatever you code, whatever you want on it. Okay. Some people for fun just code really crazy, like high-end stuff, because block coding is just coding. You can make really good stuff with block coding. Even if it looks bulkier, the ideas can be actually quite cool. So that's what I showed with my game. It does include everything code.org can do. Here's an example of one of the projects I did with my grade 9s, where they had to make a project based on circuits. So this is not the, yeah, this is right. So this one, they show us how to make a circuit. They have a simple circuit. They explain what everything is. And then eventually, I can just skip ahead. They get to a point where it's drag and drop game to figure out, okay, where do I have to put the right things to make the correct circuit? Okay. And then you can actually see inside of it all the things that they would have had to do that they made, which is, yeah, really cool. We'll go more into this. I have another session for complex projects later on, and I'll get more into how to grade this and what this looks like, and kind of how to plan through everything of a big project like this. But those are the two main possibilities for science that I think are worthwhile. Code.org Express course, where you get to pick which lessons the students do, and then the students have the background knowledge to be able to use Scratch to build something. Okay.
Sorry, you probably just looked. I just put a plug-in for Trevor's course there in the chat.
This is not free, so it's not, I don't really have a big talk about it. But you can use Minecraft. There's Minecraft for educators that's out there, which is a specific type of Minecraft where there's no online ability. This is kind of what it looks like. You have the get started, and they have courses there and lessons and so many resources and everything. Some people like Minecraft because the students it's like Lego, but with blocks. And then you can actually have specific blocks that shut on or off, which are kind of like logic gates. So you can build like simple circuits with Minecraft just by using drag and drops. And there are so many like YouTube videos explaining how it works and how to build one. And like you can just follow the steps and build a circuit with Minecraft. It's pretty cheap. If your district has a Microsoft Office like license, it's even cheaper, potentially free. Your district might have already had it and not told you about it. So that's why I just wanted to kind of mention it. You can build really crazy stuff, like really insane stuff. So that's what I have here. So like, if anyone can guess what this is just like essentially a computer. They built a computer using logic gates. If you zoomed in on these would just be blocks. These are just the little Minecraft blocks. And someone spent probably too much time building an entire computer inside of the Minecraft world, where you can add and subtract and multiply and divide and do a lot more, like it can run programs. So just to get an idea of like how extensive Minecraft can be with these ideas. It can be huge. It's just whether or not your district carries it, and whether you want to put in the work. This one's less ready to go as the others, but it is a really cool resource if you've never thought of it as a resource. I know I've had students, because they just play Minecraft, they've asked like, oh, can I use Minecraft for my project? And it's like, yeah, go ahead. So when I taught bio, I had a student run through the entire photosynthetic process as a model on Minecraft. So you as a character would walk through all the stages of photosynthesis, and you'd be able to see, and they'd be able to explain, oh, this is what this block is doing, and this is what this block is doing. So it's a really cool way to build models. It does include logic gates. It doesn't have to, though. It could literally just be a model of something. So again, Minecraft is just blocks you can play with like Legos and build whatever you want, but there is a logic gate special block that you can use in order to create different ideas. So that's pretty cool. Okay, any questions? That's pretty much it. Like that's yeah, we're about 12 minutes before 5. So yeah, we have time for discussion or questions. If you want me to go back and show you anything, I'm happy to do that. Any thoughts on Blockly? Let's see. I think I've heard, oh yeah, that's just the Google one, right? Because Google used to have, yeah, so Blockly is very, very similar to code.org. It even has some code.org based stuff. Yeah, it's nice because it does have the JavaScript always right there, but in terms of like how well it works compared to other things, I'm not sure. I've never got my students to try it. Is it, do you have any thoughts on it, Sean? You can just turn on your mic if you like.
Yeah, I'm high school.
Oh, I can't hear you, Sean. Sorry.
Okay.
Now I can hear him.
Oh, never mind. I can hear you. That's my fault.
Oh, well, that was me that time.
Oh, can you hear me now?
Yeah, I got you now.
Okay.
Yeah, like actually last year I was a junior high student. I moved to high school this year. I was doing quite a bit of code.org with my junior high students. I just found Blockly maybe a little bit more advanced for high, like a step up in advancement for high school, and a little less cartoony. So that's kind of why I gravitated towards it. And I've only done like one lesson so far with it, but it really seemed to work well with my students, and they latched onto it pretty good.
Oh, that's great.
Yeah.
I've used Blockly before, like back in my makerspace days, is that I think people would use it to code the dash and dots. And then there's Blockly, which people can use to code the Ozobots. So if you have Ozobots, what's cool with them is with the younger kids, you can do that line coding where you have like little colors that you put in particular orders to make the little Ozobot robot do different things. But then you can move up and you can use a Chromebook and you can use Ozoblockly to do the block coding with them. And then you can read it into the robot and then use it that way. So it is it's something that you can apply with little robots. But then again, now that I say that, I'm pretty sure you can do the same thing with Scratch.
And which course were you teaching, Sean?
Well, I'm just trying to get my kids like 1 or 2 credits in I can't remember the name of the courses now. But just the idea to, yeah, like we're all, including myself, we're all just beginners, just brand new. And if I can get them 1 or 2 credits towards their diploma, that's kind of the goal.
Oh, yeah, that sounds great. Yeah, and from what I can see, again, like I've only tried using coding with my junior high students. Like when it gets up there and I'm teaching mostly Chem 20, there's not super amounts of time to involve coding. Whereas junior high, I find like the curriculum is a lot more spaced out where you can experiment with stuff. But no, that sounds great. Thanks for sharing that.
And sorry, Janet, what was the name of that
Those
add-on?
robots. There's the Ozobots. So they're like little tiny robots. And yeah, the Dash and Dots are more for younger kids. I wouldn't use those with high school. There is oh, maybe someone else in here can help me. There was the one that's like a Dash and Dot that has all of these sensors, and it's better for the older kids. I will see if I can Google it. I just can't remember it off the top of my head. That's it. Thank you. Was that Linda? Yeah. Thank you, Linda. The Q robot.
Yeah, it looks like even if you just go to like the Blockly website, it has like Ozo Blockly right there, and it'll just take you to the Ozobot website where it shows how to combine the two. And like I didn't talk about it because it's hard to get backing for this, just for based on science and math. But if you can get Lego robotics kits, they are unbelievably good. They're very cool. Now, that being said, they're about $150 a kit. But if you can for like a club or something, the website is super great. It's coding on right on your browser, and you can upload it to your robot. It was the first like update they've had to the hardware system in 15 years. So like Lego does a really good job of waiting till everything is perfect to release stuff. And like that is really, really cool. If you can get
And was that
funding,
the Spike
yeah, the
Prime?
Spike Prime and Spike, yeah, for you guys, it would be Spike Prime. And if you can get funding, I do run with actually a guy named Eric DeJong, who Mark may or may not be related to.
I'm related to all of them.
You're
Thousands and thousands.
thousands and thousands, yeah. Yeah, so I work I TA there in the summer, and it's a 1 week. I've had teachers from our district come and like just do the 1 week. It's 1 week all day for 5 days, but all you do is play with Lego robotics and then make projects. And it's really, really fun. If you can get into that class, it's usually blocked at like 16 people, but if you can get like the funding from your district to do it, I would highly recommend it.
We got a grant for some Vex robotics kits. I don't know if you guys have heard of Vex at all.
Yeah.
They run about $3,000, but anyway, so speaking of getting credits like you, Sean, I'm in a high school, but yeah, so it's really cool. It's essentially mechano kits that kids build and then they can control by remote control. There's a pneumatics set in it, but then you can automate them through coding as well and send them to competitions. But so we've been really lucky. But for me, I just came to this because I know nothing about it. I just sort of set the kids who are slightly on the spectrum onto the project, and they're devouring it. So it's been really, really cool. Yeah.
Yeah, that's awesome.
Yeah, that's something, Sean, you might want to look at as well, is the Vex robotics. And then is it robotics first that is where the competitions are?
It's
for those?
yeah, it's the first Lego League, FLL,
Mm.
first Lego League, and they have competitions where you like get a mat, and then you get a board, and like everyone can copy it, and then you build robots to do certain tasks, and every year they switch it, and then depending on which tasks you do, you get certain points, and it's really, really fun, and the students get really into it. But yeah, that's only for the Lego robotics, but it looks like Vex has something very, very similar to that, where
Yeah.
each robot has to do something specific. But yeah, it's pretty cool. Any other question? Oh, yeah, go ahead.
So, if you can't tell from the wall behind me, am the music teacher. And this year, one of my grades has been it's a smaller class, so they combined them. So instead of having two music classes, I only have one music class with them. And so they wanted me to teach computers. So yeah, you're basically talking to like a kindergartner. Yeah. So where should I start with? Like, should I just go to the CS one that you were talking about? Like, which one's the easiest that I'm going to be able to handle?
For long-term, just do the code.org program. Just give the kids Chromebooks, allow them to run through. You would set them up with a classroom similar to like Google Classroom. So you would have a code for them to join a classroom. They would join, and then you'd be able to see everyone as well as everyone's progress.
Right. So the one that is code CODE in black squares with the turquoise. Okay.
That would be the best place.
And just do the
Starting at
accelerated
0.
intro to CS course. Do that one, the accelerated intro one.
Yeah, that's exactly
Because
where
they're going to be grade 7 kids. So
I think that's perfect.
okay.
Yeah. It really incorporates kind of everyone, like the kids that already know it, they'll just blow by the first however long, right? But for the kids that don't, they'll still be moving quickly, but it'll give them a chance to actually play with stuff. And like there is a part in every unit where it's like, okay, now you have like a playground, try to build this, and it'll give them like kind of a project. So as a place for like where everyone's starting at 0, that's what I would probably recommend.
Perfect. Thank you.
Yeah, no problem.
I also recommend like the doing things with the little robots, having kind of those robot challenges. They're just so it goes back to what Braden was saying about that constructionist. Like it's so hands-on, being able to consider how something's going to move, but instead of just pressing a play button and it being online, you're actually moving a robot on the ground, like those kinds of things. That's sort of a whole other thing. Trish has a comment in the chat too, saying that she brings them to grades 1 to 3 for, I'll read it out because of the recording. 1 to 3 for surprise activities all the time, and also taught a junior high coding option. The elementary seem more willing to take risks. I'm curious if others here agree with that, because I do. They talk out the problems to solve. Any suggestions to bring the risk taking to junior high? Have you done Makey-Makeys? Has anybody here used Makey-Makeys? I remember hearing of some junior high kids just having a blast with them. They're these little, they're a little bit like microbits, and actually microbits maybe even better. Where it's like a little circuit board, and you can sort of, you could do music with them. It would be a great way to take music and computers and put it together, because you can make like cardboard guitars and pianos that you walk on and like things like that.
Yeah, Janet, I did the banana, and
Yeah.
cool. But then I'm like when I go into the classrooms, I'm a diverse learner teacher, so I get an opportunity to support kids K to 9 in my school. I just don't see, they want to play, and I don't want to say goof around, because I want them to experiment, but I would bring in like a piece of celery, and we would hook a banana up, and I'd show them the tunes, and I'm like, I can't seem to catch them. And then I have all the boys, and they ask me questions, and I'm like, okay, guys, let's figure it out together. Who can help me solve this? I don't know if it's because I'm female and I have mostly males. Like the kids are nice, but I need the hook is what I'm looking for. So it looks like there's a lot of guys here. So do you have a special hook or suggestions you can help me with?
Just off the top of my head, it was what got them going was performance-based. So they created this robot, they created the everything, and then I said, okay, so I want to film this robot in action in the school for our Instagram, and I need to see it performing some tests. So right now we're doing a sock drive for leading into Christmas, and I want to see the sock drive promoted with the robot. So I need the robot collecting socks and dropping them into the deposit box, so that so on, etc. And so they automated the robot to do that, and with immense failure over and over again. And I had one of them filming it, and then finally they had created a project filmed and ready for our page, kind of thing. And so that was, I guess, kind of what got buy-in and risk-taking there. It wasn't super public because it was the four of them, you know, trying to figure out this thing, but then it became public and something they were proud to show everyone. I don't know if that helps you at all.
I love that all the attempts and the failure and learning from that, and yet that part not being public. So there's no risk. They don't have to feel bad about that. They just work through it and learn and showcase the good.
Yeah, I'm not sure if like my context, Trish, is I'm a male and I teach 2/3 female. So we are in like exact opposite exact opposite position. So if you can tell me how to get a positive attitude from a grade 7 girl, I'd appreciate it.
Thanks for all the help, you guys. I guess we just all need to keep trying and moving forward with everybody. Thank you.
Just a quick question. When is the next course that you were talking about where you talk about
Oh.
how you're going to mark things, and when's that course happening?
So I have 2 of those. There's simple projects for Div 2 and 3, and that'll be January 22nd.
Okay.
And then I have more complex, so that's more like the one I was showing you with the circuits. That'll be on February 5th. And that's more focused on Div 3.
I don't know what Div 3 and Div 2.
Oh, like Div
7
2 is like grades. I work in a K-12 school, so we have like the different divisions.
Okay. Yeah,
Div 3 is junior high, and like Div 2 is 4 to 6.
So if you just see, I can just put in the chat, but if you just go to erlc.ca and then just right at the top where you can search it says search by title, facilitator, keywords. So you can just say Braden Cagle, and then it will bring up all of Braden's stuff. And then you can just click and register.
Okay.
Yeah, so with those presentations, it'll be getting more into like rubrics and curriculum, and kind of why making artifacts is actually easier than what you'd think. And then like also some reflection stuff. So it's going to involve, yeah, basically how to implement it and like just some basic ideas for what the projects could be.
Okay. Perfect. Thank you.
Yeah.
Well, I'm going to stop the recording. Stop.